So I would just go through the list alphabetically as it was online. So I would just start with Santiago Gavila. Please unmute yourself and share your slide. You have 1 minute to remind us of the topic.
Thank you, everyone. Thank you for the organizers for giving me this opportunity. So, yeah, summary of the talk is on this slide. So basically what we did in this talk and this paper is to analyze the galaxy halo connection via the halo occupation distribution, and we applied that for the mission line galaxies and EVOS data. So we studied how the detailed choices of the mean halo occupation distribution can affect galaxy clustering, but also how the satellite probability distribution function can affect it, or how the way we put the positions of satellites or their velocities change the clustering of the ELGs. This is motivated by previous theoretical and simulation studies. And what we found is that these details, which goes into the profiles of the PDF, can affect more the clustering than maybe the mean halo occupation distribution, which is what people usually focus on. We found that a robust evidence for under-concentrated profiles for ELGs on the EVOS data. And also we find other fits, but this is the main result. What we find also is that the galaxy clustering can be affected even on cosmological effects and potentially in the inference of cosmology. We saw that this was negligible for EVOS, but since we are going to new surveys with more data, more statistical power, and going to smaller scales, we will need to revisit all these details for those surveys and check that this is working still. And especially because we will be looking at the vision and galaxies with Euclid and DESI. And in case you want to use them for your study, you can download the box here. So that's the summary.
Thanks a lot. So we open the floor for questions. Anyone? It's your turn now. We had the number already, of course, in Slack, which we might also come back to. I don't see anything at the moment, so I would just come back to some of the questions.
Sorry, Robert, I would like to ask a question, but I didn't know how to actually ask for it, so I just unmuted myself. I hope it's
I think you
okay.
Found it now. Okay, go ahead, Marcus.
Okay, so Santi, actually, I keep wondering, like, you use this HOD, right? Like halo occupation distribution to study all of this. But I mean, I have never worked with like deeply with HOD or SAMS, but I don't know, would this be very different if you would have used something like SAMS? I don't know.
I mean, it would be the same. I mean, it wouldn't be the same, but so the idea here is we were using a simulation that was only having friend-to-friend halos, so we basically needed to use halo occupation distribution models. If you have subhalos, then it gets more interesting to use some sham with subhalo abundance matching. So we could also study something there. But I think what we found interestingly is that, I mean, it's not only, how you populate them, but also, I mean, all these details, yeah. If you have shams, maybe you don't need to decide that much of the position and velocities, but of course, a similar study could have been done. I don't know. It would be nice to explore as many models for galaxy assignment as we have, right?
Yeah. I mean, I was asking this because, well, I mean, because from SAMS, I guess you have like different free parameters, and it was kind of like a question about like what is the physical meaning of your findings, basically, kind of like that. I think I missed that.
So, I mean, it depends on what part
Let me just quickly interrupt, because I think we have quite a number of questions, so we might come back to it at the time.
Later.
No, of course, it's very interesting. I mean, just like, if we don't have a time, you can, of course, always discuss afterwards more details. So I think Oliver was next. Please go ahead.
Yeah, thanks. Yeah, okay, so the question I had is, so it looks like from your findings that as you vary some of the HD parameters, you get noticeable biases in some of the parameters, like the Yarkov-Chinsky ones, or at least biases which would be noticeable in the future. So what's that physically telling us? Is that telling us that the bias parameterizations we're using aren't flexible enough? Because it feels to me like the bias parameterization should be able to account for any HODs, etc.
I think we need, so once for doing a cosmological analysis, you need to make a lot of decisions. What is your K-max? How many beams you use? And I think it depends on all of that, number density that you're using. So you have to do it for a specific survey. So what we showed here is that it was not worrisome for EBOS because of the statistical error bars. Once you kind of aim for a specific model, you have to check again for a specific survey. And of course, it depends on the bias you put on this the prior you put on these parameters, because maybe you need to enhance the freedom of those parameters. I think some of the parameters in this particular case were fixed to some perturbation theory predictions. So maybe in the future you need to open it a bit of space, I think.
Okay, thanks.
Christoph?
Sorry, yeah, please, Christoph, go ahead.
Yes, so my question is why you're specifically focusing on ELG. So maybe it's just my DESI head, but I know that the ELGs will be very poorly sampled, and I think you won't have many ELGs in the same cluster. While, for example, in the BGS, you would have many galaxies in the same clusters.
Well, it's one of the main tracers that will be used for, well, that has been used for EBOS, and it will be used a lot in DESI and Euclid. So all the clustering will be based on H-alpha emission and galaxies of the spectroscopic ones. So that's why we want to understand this better. First, because this was also done in the context of EBOS, but I think it's also very interesting to upcoming surveys because they will rely on this kind of galaxies. So if there is any physics of the galaxy formation behind all this connection, I think the more we learn, the better we understand also the cosmology, not only the galaxy formation.
Thank you.
All right, thank you. Maybe related to that, on the Slack, there's also some discussion about specific, also again, like different discussions about the emission line galaxies regarding, first of all, like, can there be the satellite galaxies or central galaxies, robustness compared to observations? Maybe you can just say a few more words on that since we're on that topic right now.
Yeah, so one of the questions was related to whether ELGs can be satellites and centrals. So the thing is, in very massive halos, it's true that you won't find emission line galaxies at the center of the halos. But if you go to smaller halos, yes, because those halos will be younger, let's say. So that wouldn't have any problem. So the occupation so goes basically, this has a peak in the one that we are using. You can go to slides and check it, but we have a peak in a mass around 10 to 11 or so, and then it decays. That's why, because basically at larger scales, you have these star-forming emission line galaxies, but you do have satellites in that case.
No. Yeah. Again, anyone has some question, just raise your hand or text it to Nico. I was wondering, so I mean, you mentioned, I think we have one question by Louis. Please go ahead, unmute yourself.
Yes, so I already asked you a lot of questions, Santi. So, but just to be sure, so when you vary satellite fraction, when you fit EBOS data, you fix the cosmology, but you didn't do a fit where you vary all parameters, including the satellite fraction and the HRD parameters.
No, when we fit okay, sorry, maybe I misunderstood your question before. So we're trying to fit in this paper for the HUD parameters, the cosmology was fixed because we were always using the outer ring simulation and everything was fixed to that cosmology because, it was also like we were not doing a theory prediction, we were actually making mocks, computing the correlation functions and then checking with Equinox data. So within this setup, it will be complicated to do all the cosmologies. But I mean, maybe with the setup that Marcos is commenting on, probably you can do it because you can also vary the cosmology. And on the other hand, maybe I was answering you when we fit for cosmology for BAO and resist space distortion. There you have the bias parameters to take care of all these details of like a finger of God effects or things like that.
Okay. So you didn't use HOD to get cosmological constraints? No,
it's not.
Okay.
It's not that. It's more like a perturbation theory with nonlinear bias, etc. Like
okay.
a similar kind of modeling that Marcos was presenting. I mean, it's also in the slides. Some slides the model we're using, and it's the reference is the paper the Mati data 2021. So that's the one that we use the same pipeline it was used for the data on the MOX, but it's not based on like a Halo model. It's not a Halo model based theory.
Okay, I think we have a bit less than a minute left. Maybe since in the end of your talk you mentioned that because of the currently the systematic uncertainties of this are still small compared to the statistical ones of the available data, but that will change with the stage 4 experiments. Can you try to predict, guesstimate a bit like how relevant it will be compared to those? If you can, I don't know.
It's complicated. I mean, I'm working also in these collaborations, and of course, there's the people are working in more evolved techniques and like doing, I don't know, working with emulators or or improved theories. So it depends. I mean, in the end, we will need to check all these new tools against like all new mocks and make sure that within the choices we make, like scale cuts, priors or nuisance parameters, then we can recover always the same cosmology if we only change the galaxy physics. So we will need to check for that. It's a complicated effort, okay. I think.
That's fair. That's very fair. Thanks. So I think we're out of time then. Thanks a lot again, Santiago.
Okay, thanks. I will be in Sococo then later if someone wants to discuss more.
Then let's continue alphabetically. I have David Harvey next, so please unmute yourself, share your quick summary slide. Perfect. Well, you have a minute.
Great.
Go ahead.
Thank you very much. Yeah, so very quickly, intrinsic alignments. Galaxies that form in the same environment will have their shapes correlated as the torque, the tidal fields pull and torque the galaxies. They shape and form in the same similar way. And intrinsic alignments are often seen as a nuisance parameter in cosmic shear studies because it means the galaxies aren't randomly aligned, that you often assume. And often you have to model for these nuisance parameters. However, they also could be sources of signal because if you change the dark matter distribution, then you'll change the intrinsic alignments of these galaxies. And the fundamental properties of dark matter, if you change the fundamental properties, they will also change the density field and thus the intrinsic alignments. So what I did is I looked at how self-interacting dark matter would change the intrinsic alignments of galaxies. And what I'm showing here is we measured the correlation functions between the shape of centrals in galaxy clusters with all the satellites. And we then fitted a power law, which consisted of a simple amplitude and power law index, and measured this over all the centrals and galaxies in the n-body simulations that we have. And we found that the amplitude and the power law index were a function of the cross-section. So specifically the dark matter self-interactions, because they would reduce the density of dark matter in the clusters, they would make galaxies more spherical as well. That would suppress the intrinsic alignment signal, and also change the...
David, I have to ask you to wrap up so we have more time for questions.
That's it.
Perfect. Great. All right. So any live questions immediately? If yes, please, Marcus, go ahead. Marcus, you're still muted.
Okay, David.
Yeah.
Okay. Thank you for the talk, David. And yeah, can you hear me?
Yeah, I can hear you.
Yes.
Yeah, you're good. Go ahead.
Okay, sorry. So thank you for the talk. And I have like one further question, which is, you mentioned that this effect can be decoupled from baryonic effects. Is that true?
So we looked at a couple of different variations of baryonic feedback to see whether we can mimic it. And it's the baryonic feedback seemed to change the amplitude, but not the power law index. of the correlation function, and the amount by which it was altered was still within you could still get some useful information even with the current constraints of baryonic physics. So they didn't change it too much. So on one side, the baryonic feedback does mimic it to some extent, and you have to worry a little bit, but it's not a huge impact, and you could potentially use the power law index of the correlation function to try and break that degeneracy.
Okay, thank you very much, David.
No worries.
Yes, Cora, go ahead.
So that's maybe a bit of a naive question, but I remember from your talk that this happens on very small scales. And I was just wondering, what is this arm measured, I guess 100? So what kind of physical scales are we talking about here?
Okay, so yeah, it's a good question. So this R measured corresponds to the scale of the galaxy you're measuring the shape. So this is 100 kiloparsecs, but that's not the scale of it. That's the yeah. So for example, when you measure a galaxy in Euclid, you'll be measuring it on a couple of arc seconds, which will be of order about 100 kiloparsecs. So of that galaxy, but we fit the power law indexes from 300 kiloparsecs, co-moving kiloparsecs and above. So we fit it down to 200 kiloparsecs, co-moving over H. So yeah, you're right. A lot of the discrepancy power of the different cross sections come from less than 1 megaparsec.
Okay, thanks. That helps.
No worries.
Okay. If we don't have any immediate questions, maybe I want to come back to something on Slack, which was related to the first question with the baryonic effects, but maybe even beyond that. Could you maybe also say a bit more specifically what, so there's this one effect that you have, for example, baryonic effects or anything else, maybe modified gravity that can directly also appear in intrinsic alignments. But of course, you don't observe intrinsic alignments directly. You always observe the whole thing in addition with the actual lens signal. So how could that add any additional degeneracies, maybe some effects in this lensing signal that would obscure these effects potentially?
Well, if you have spectroscopic redshifts of your galaxies, then you can pick galaxies that are all the same redshift. So theoretically, there should be no. And if you pick low redshift galaxies, so they're quite close to you, then theoretically, the intrinsic alignment signals actually dominates over the cosmic shear signal. So you can be clever with your selection. I'm not an expert in modified gravity. I'm sure that modified gravity models will suppress the intrinsic alignment signal in a similar way. It's always the case with dark matter, changing the dark matter distribution or changing the laws of gravity. Often you can do similar things. So you would obviously combine this measurement with other predictors of self-interaction dark matter to really confirm that it is that happening. But the nice thing is that this is one of the like often self-interacting dark matter measurements are taken from profiles of clusters or from strong lensing of the intricate details of the core and those things. Where this is a much simpler, much simpler measurement of the self-interaction. So, but yeah, you're right. There will be some degeneracies with modified gravity.
Just like regarding your point, we're focusing on the same redshift, but you still have the galaxy lens correlations in there still. I mean, you wouldn't get rid of those then, right? You would get rid of different galaxies at different redshifts, but you would still have the correlation with the lens. You couldn't get rid of that, right?
You mean the lens for
the correlation with the of the source of the lens, basically. I'm not an expert on weak lensing either. So.
Well, I mean, I guess the point is if you, because you don't, yeah, I guess you don't have a lens. There's no lens sample here, right? This is just you just have because this is not lensing we're doing here. This is
no. But I'm just thinking about the types of observations you would get the most, where we would see these effects. No, I know that.
Yeah, I mean, it's interesting. I mean, it is interesting because We didn't look at a huge range of redshifts in our study, so it would be interesting to look at higher redshift to see if there was a better, more signal. But as you said, you wouldn't want to go too high because then your lensing signal gets very high. So you'd have to pick very low redshift galaxies with spectroscopic redshift, so you wouldn't get any dilution like that. But yeah, as far as I can think, there would be no kind of contamination from any lensing effect if your galaxies were low enough redshift. Like I'm talking like redshift of like 0.1, 0.2 here, like
yeah,
very low redshift.
Very low. Okay. Thanks, Cora.
I was wondering, what kind of galaxies should you look at here regarding morphology or color? Because intrinsic alignment models, right, are sensitive to what kind of morphology or I guess color you have.
Yeah, I mean, I guess the majority, I mean, when they do studies, right, they find that the majority of galaxies, these red galaxies are aligned, but blue galaxies are not, right? In this situation, we're correlating the centrals in massive halos. So the majority of the centrals are in halos of over 10 to the 14 stellar masses. So they're basically BCGs we're talking about here, correlated with mostly their satellites out to about 10 megaparsecs. So those galaxies are also going to be like red sequence, spherical, big galaxies. So that's where the signal will be. So in terms of your choice, I think that's what you'd have to look at. Now, I'm no expert in selections of large-scale galaxy surveys, but that's what we looked at. So that's what you would. So that's how we'd have to compare directly to observations.
Okay. Any other questions at the moment? If not, in Slack, there was also there's some questions about the types of dark matter models to consider, given like the velocity dependence or not dependence of the self interactions. Maybe you can just say a few words about that.
Yeah. So in these plots here, I'm showing four dark matter models. You've got just collisionless dark matter, and then you've got 3 types of elastic velocity independent dark matter, but we also simulated a velocity dependent dark matter model. So that's kind of like if you've got some kind of Yukawa potential, and then you've got like at low velocities you have a velocity independent, but then at high velocities it's v to the minus 4. Because this is quite a common model that's now used in self-interacting dark matter, since clusters of galaxies, limits in clusters of galaxies are very tight, whereas in dwarf galaxies they're less so. So that's what we simulate. Now the velocity dependent cross section acts very similar to a velocity independent at 1 centimeter square per gram. So there's not much difference between the two of those. So it's often no need to really to do those simulations. But yeah, we just do it on that. And then the kind of scattering that's involved in the simulations, you have elastic isotropic scattering, so that when 2 particles come close together, you just have some distribution which it'll scatter off with some probability.
So deliberately not trying to pick a very specific model, but having like a broad class of characteristics that you could constrain. Yeah,
I mean, when you do these simulations, you've got particles that tend to 9 solar masses, so you can't get. I mean, it's just a very simple way of mimicking the scattering. And then you can then try and infer your particle physics models from there. But no, there's no way, unless you've got some very intricate simulations that are solving quantum equations.
No, of course.
It's just very simple scattering.
All right, great. So with that, I think we're out of time. And Nico also friendly reminded me of that right now.
Well, thank you very much for giving me the chance to show my stuff.
Thank you. And then I would move on to who's next? It's Marcos Parejero Ibanez. Please share your reminder slide with us.
Yes, 1 second here. Can you see it?
You can see it.
Yeah. Perfect.
All right. You have a minute.
Okay.
Everyone else.
Yeah. So my talk was the very poorly edited one, and it was this one that, based on some prescription to go from dark matter over density field to galaxy over density field in the initial conditions of space or in the Lagrangian space, then you use an embody simulation to evolve this over density field. And this actually is able to give you very, very accurate results, at least at the 2-point statistics level. Actually, we can see here, like in comparison to galaxy-like MOCs, and but since it relies on an embodied simulation, it actually is very slow. But we sped it up by means of scaling algorithm and a neural network, and we were able to actually produce some theory, some model that is fast enough to do cosmological constraints, and it's based on these large-scale bias expansions. I think is the most accurate to date. I might be wrong, but I think it is.
Great. Thank you. So this floor is open for questions. Please go ahead if you have any. And again, I remind everyone, if you don't feel comfortable, just send them directly to Nico. Otherwise,
Yep.
I was.
You can ask me anything, anyways. Like I will never think it's a dumb question. I will feel dumb if I don't know how to answer that. So feel really comfortable on asking me anything.
All right, cool. I'll go ahead.
Okay, I will take your invitation. So my question might be very general, right?
Okay.
I'm not sure whether it would be dumb, but so essentially my question is here, what is the kind of underlying physical assumption, right? Is the assumption that the shape of your bias model basically is the same no matter which cosmology you are in? Or so what is basically the split between the cosmology and the bias model here?
Mm-hmm. So, okay, so it is, so the prescriptions, like this mapping between, like this bias mapping is assumed to be the same for every cosmology. What changes in each cosmology are two things, right? These linear over density fields for the dark matter, because, well, depending on if you have like higher sigma 8 or lower sigma 8, of course, this over density field changes, and also on the growth, right? So, and that growth is actually encoded in this embody evolution, right? So yes, so the question on whether this mapping depends or not on the cosmology is a very good question. I will say it doesn't. What it does, it might be like as I was saying, like the overdensity field, and maybe like these free parameters, right? Like these nuisance parameters that in the end we will try to marginalize over. But the truth is that, yeah, maybe the mapping is different for different cosmologies. Although I would be very surprised, because this mapping is actually like a choice of basis, if you want to think about it in this way. Or in another way, it's kind of like telling, look, the galaxy over density field will be something like a Gaussian, like because this delta is Gaussian, and then some modifications to that Gaussian. So for example, it's been shown that if you put like a threshold on your density field, then it should depend on the large scales, on delta, delta squared, delta cubed, and all those. And we include like these tidal field terms and these Laplacian terms because they are also like possibilities that you can include, and that they follow the symmetries, the Galilean symmetries of the problem. So yeah, I don't know if I explained myself good enough or my answer was dumb.
No, I think it was a good explanation. Yeah, in some sense, you're saying we don't quite know whether B1, B2, right, are truly cosmology independent, because in some sense, right, it's scale dependent, and the scale dependence could come from cosmology. But that helps. Thanks.
Thank you.
So we have another question from Bernard.
Hi, Marcos.
Hi.
Thanks for your talk. I will ask you if a third order term in the bias expansion, do you know how it may affect?
Actually, I don't know, because we have not included them yet. But I know that, I mean, like the fits will be better. So if we are within 1% now, then we will be within, I don't know, something. I mean, as long as it's not noise, we will be like even better than that. The problem with that is that including third order terms actually includes several extra bias terms, right? And they are more nuisance parameters that you want to marginalize over. And if in the end you're interested in cosmology, what they are doing, if they are not helping that much, is actually making your contours, right, in parameter space larger. And that's something that you don't want. You want like the minimal model, right? So yeah, that would be kind of like the
Okay,
reason. Yeah, sorry.
Then for the future surveys of the precision of the future surveys, the third order term will not affect. I understand.
I mean, it might, but the errors that we are showing here, for example, in this lower panel, they are actually Gaussian errors. So they are very infra-estimated on small scales, right? Because we are not taking into account nonlinear effects that correlates different modes, right? So I will say that at this point, I don't think there's going to be the need of third order terms, but I cannot tell that for sure.
Okay, thanks.
Okay, great. We have a couple more questions. So first one would be by Simon. Simon Foreman, please.
Hi, Marcos. Have you thought about doing this for the bispectrum? Seems like the same approach should basically work.
Yes,
it would be more difficult. But
we have.
Wondering.
Actually, we have tested the bispectrum, and it gives very good results too. But we're still lacking like a full study, because it is easy to. I mean, what we did was this super simple example, which is. I mean, we get these fields, we evolve them to Euclidean space. We get the bias terms from the 2-point statistics, and then with those bias terms, we get we come back to the field, to the galaxy field, and we compute the bias spectrum there, and then compare. And it looked very good, but one has to be careful because the bias, for example, like there's like a extra source of noise when you do bispectrum. And in here, I didn't mention this, but we are taking into account like some Poisson noise that is not maybe like the best way of actually taking this noise. So actually going to the bispectrum, that might be even worse. And one needs to study this in a little bit more detail. But the results we have right now are actually encouraging. They look quite good. And we're working on that. I think we will have like some, I don't know, some paper in some months from now. I cannot tell you. I cannot tell you exactly because I'm not first author of that paper. So it's kind of like I depend also on the first author.
Great, thanks a lot.
All right. Next will be by Azadeh.
Thanks, Marcus, for the talk. But I have maybe one comment on the previous question that was about the third order biases. Maybe I think it's it's helpful to see whether, let's say, for the Boss analysis that Ivanova family did, I think their conclusion also was that the third order bias, because it's very degenerate with the second order tidal field bias, then there is basically no constraining power if you allow it to be free. But for instance, in the context of Euclid, on the Euclid simulations, we have been testing this, that let's say if you allow but all of the biases up to third order to be basically free, you see these huge degeneracies, and then your likelihoods will be these multimodal likelihoods, and everything looks really bad. And then assuming, I think, perhaps what I can say is that assuming maybe the biases to be related would be a good thing to do if you only have power spectrum. Now, with that, I wanted to ask you whether, for instance, you have tested, let's say, with your framework, how if you assume these biases are related to one another, it will change, it will affect the power spectrum or bias spectrum, or
Right. Actually, thank you for the question and for the information before. Actually, I didn't know about that, so super thank you. But okay, so
Marcos, let me just quickly tell you. I just have to ask you to try to make it short. You have to move on.
Sorry.
Just let you know.
Okay. Sorry. Okay. So super quick. We are working on finding what are like the best priors for this bias over a range of many galaxy MOCs, stellar mass selected and star formation rate selected. Okay, and with that we will be able to give a relation between B1 and B2, B2 and BS2, and so on. So yes, we're working on that, and soon we will have some results about this. Yeah.
Thanks. That will be very interesting indeed.
Great. I'm afraid we have to move on. Sorry, Santiago, but of course there's plenty of time to discuss further questions after this. So thanks again, Marcos,
Thank you
for answering all these questions. So next would be Oliver Philcox. Please share your slides.
Sure. There we go. Cool. Okay, so 1 minute summary is that some new developments in algorithms for measuring cosmological correlation functions now enables us to measure the 3, 4, 5, 6, 7 up to infinity point correlation functions in quadratic time. So it doesn't depend on the number of the endpoint function, which is great. So we can now measure all these things super quickly, and we have public code to do it. So in the last couple of months, we've basically been thinking, now that we can measure these things, what should we do with them? So one aspect of this I discussed was that we can measure the non-Gaussian 4-point function of the boss galaxies, and we get an 8 sigma detection of that, so it's pretty strong. There's a couple of subtleties to actually making that detection. We need to know quite a bit about compression and theory models, but there's a lot of other future applications as well. So other applications would be detecting other forms of gravitational non-Gaussianity in higher point functions, maybe even inflationary non-Gaussianity like FNL, tau NL, etc. Other things include tightening parameter constraints from our standard theory models, and also testing more exotic physics models like cosmological parity violation is something that we can in fact only detect if we use 4 higher point correlation functions. So that's a 1 minute summary, and I'm happy to answer any questions.
Thanks. So there already has been plenty of discussion on Slack, of course, but I think there's still more to be discussed. So if there are any questions now, please raise your hand or write Nico. Otherwise, yes, Cora, of course.
We'll shoot with a question that just came to my mind now. So one test I had in mind, so let's assume we have a simple density field, right? Let's say log normal, because it's a cute test case. Usually you would say, okay, if I have a log normal field, roughly speaking, extracting 2-point information and like the 1-point PDF should allow you to extract more of the information, but still you should basically expect to increase your constraints by looking at the higher orders, right? Because even if there is some relation, the more you measure, the more you will kind of reduce your error. So I was wondering, what kind of your formalism do you think that would allow you to test a simple case like this?
Yeah, absolutely. I think that's certainly very possible. And something we're looking at the moment is using simulations to kind of quantify the information content as we increase, as we go from 2 to 3 to 4-point functions. Log normals are a good example, I guess, as a field that has an endpoint function at all orders, which is non-zero. So yeah, it's certainly something we can test.
All right. Do you already have some expectations on like at which point gain information will be limited just by observations? Like,
yeah, it's a very good question. So one thing about higher point functions is that in terms of constraining lambda CDM parameters, they're actually most useful at low redshifts, simply because as you go to higher point functions, they really fall off as you go up to higher and higher redshifts. And actually, so thinking when we go into like the era of DESI, we're thinking the volume of these surveys is going to increase by kind of tens to hundreds of times. But in fact, the amount of information in the higher point functions doesn't increase by anywhere near that amount, simply because most of the observations are at a lot higher redshift. That said, it is likely we're going to be able to detect all these things at least twice the significance we can now. So it's looking like there will be quite a bit of information in there. Exactly how to extract it is another question.
Of course. Oh, that sounds promising. All right, we have a question by Azadeh.
Oliver, hi. So I have one question. In your talk, you had one slide that was comparison of the power spectrum, bispectrum, and trispectrum, I think on Quixote simulations, if I remember correctly. But one thing I noticed is that you get a significant improvement when you add trispectrum, while going from power spectrum to bispectrum, the improvement is not so significant. Do you have an idea what the trispectrum is really bringing that is helping so much? Because I found it quite interesting.
Yeah, so I think this is the plot in particular of this. That's a very good question. I think one thing, I would take these results a little bit with a grain of salt at the moment. So there's always a danger of showing results which you haven't quite finished with. There is a problem that the 4-point function is inherently very, very noisy. And an irritating feature of Fisher forecasts is that noise happens to look like extra constraining power on observations. So the 3-point function is very converged here. The 4-point function is not quite. In fact, we're currently running more and more simulations to try and assess the impact of noise on this. So it is slightly possible to be somewhat over-optimistic. In general, exactly why it's more constraining, that's a difficult thing to answer. I think part of the thing might be that this is kind of a magical effect based on the fact that these simulations, kind of the HOD parameters they're scanning over, aren't really free enough to represent the real universe. So here there's 5 HOD parameters. So basically, once you just have, say, the 2- and 3-point functions, you still have quite a bit of degeneracy left. But by the time we've gone up to the 4-point as well, we've really nailed down all 5 of those parameters. So you can basically just keep on getting more and more gains on cosmological parameters. Whether that's true or not is a difficult story to quantify, I think.
And here you go to K max of like.
Yeah, so this is all in configuration space. So it's basically down to a minimum radius, 20 megaparsecs.
I see. Yeah, I didn't realize it was.
Yeah, but we can easily adjust that and try other things.
Cool, thanks.
Great. So there was another question by Alex. Please go ahead.
Yeah, I just wanted to ask, could you use like a direct measurement of the 4-point function as a sort of cross-check on the non-Gaussian part of the covariance matrix for the 2-point function? Is that something that you'd ever want to do? Is that something that would ever be useful? Yeah,
that's a very clever idea, actually. So I guess the idea is that the covariance matrix of the 2-point function contains a piece involving 2 2-point functions and a piece involving a 4-point function. Yes, it's in fact a very specific 4-point function. It's one in which 2 of the legs are collapsed in a specific way. But yeah, one could absolutely do that. And that would allow the full 2-point analysis to be done from so ideally, I guess, from the survey itself, although it does introduce quite a bit of noise because the 4-point functions from your survey are inherently very noisy.
Yeah. Okay. So I guess you also miss the super survey mode as well.
Yes, that is another point.
Okay.
Yeah.
All right, right. Next would be Daniela.
Hello, can you hear me?
Yes.
Yes.
I have a bit of a speculative question. Can you imagine, so one of the reasons why the endpoint functions haven't been used as much as they could have is that we don't always understand their systematics. So I was wondering, can you imagine using the n+1, n+2, and so on correlation function as a way to reduce the systematics on the the endpoint function? So for instance, that would mean using the 4, 5, 6, etc. point correlation function in order to have insights on the systematics plug in the 3-point correlation function.
Yeah, that's a very interesting question. I think it's certainly possible, although I think there is a danger of, if you're trying to measure the systematics of the 2-point function with the 4-point function, does the 4-point function have much more systematics in to start with? So it's not particularly straightforward. However, I think there certainly are sort of consistency checks you can do with higher point functions for systematic effects. And actually, I think a nice one is actually part of the 4-point function. There's 2 contributions, one of which is symmetric if you reflect the whole universe, the other of which isn't. It's this parity violating bit. And in fact, assuming that you have no funky physics going on, that is actually a very good test of your systematics, because your 4-point function should be invariant under mirror flips or parity inversion, but systematics can cause that not to be the case. So in fact, that is an example in which you would be able to use these higher point functions to test for that, and that extends for higher statistics as well.
Actually, this is very interesting, and thank you for your answer. There's just something that I wanted to,
Daniela,
to answer.
I'm sorry, I think we have It'd be better if you just discuss it afterwards.
I think that you had some problem with the audio. I don't know, maybe it was just for me. But now we should be fine.
Okay.
Okay.
Fine now? Okay. Okay, good. Please unmute yourself.
Sorry, Robert, your audio also dropped out for me there.
I'm sorry. Is it better now?
Yeah, that's better.
No, but I was just, so if you can hear me now, so I wanted to ask Susan to ask a question. Oh, yeah, now it works. Okay, great.
Okay. It's just a question of fact I want to ask about. When you work out, do your Fisher forecast and do your covariance, do you do the cross covariance between the different?
Yeah, so that's an important thing actually. So quite a lot of the forecasting we've been doing has been using Gaussian approximations to the covariance matrices, basically assuming for the purpose of the covariance, we only have a 2-point function. So in that limit, there is 0 cross covariance between all these things.
Yeah.
So in fact, one thing I have been trying is sort of using some data compression techniques and then actually getting all those covariances directly from simulations instead. And the benefit of that is then it does account for those cross covariances between the 2 and 3 and 4-point functions. And we found, this is again, very much preliminary results, but we found very similar contours in that case. So it doesn't seem to be a big impact.
No, but it's what, so I didn't realize you'd assumed they were Gaussian.
Yeah,
so your results were Gaussian, but yeah, okay.
Yeah, so that was just to get an analytic.
But it's worth checking, isn't it? That it's.
Yes, oh, absolutely.
Yeah, okay, thank you.
All right. Great, we have to move on. I hope you can hear me right now. If not, okay, great. So sorry to Simon. Just have to get in touch with Oliver afterwards in the discussion time. So we come to the final speaker of that session, Kia Rogers. Please share your slides. Slide, singular.
No problem. Okay. Can you see that slide?
Yes, everything's fine.
Perfect. So I'll just show the kind of main results slide from the talk. And so in this work, we used the Lyman alpha forest, which is a absorption feature in the spectra of high redshift quasars. And if you measure the correlations within those absorption lines, the power spectrum, you have a very good tracer of the linear matter power spectrum. And so we use the Lyman alpha forest flux power spectrum to look for signatures of deviation from cold dark matter, in particular if the dark matter was comprised of ultralight axions. And in that case, you get this very sharp cutoff in the linear matter power, which in the flux power manifests as some slightly less sharp suppression relative to the cold dark matter limit. And so in the talk, I talk about the methodology. And so in particular, you have to use hydrodynamical simulations to model the forest sufficiently accurately on small scales. And we constructed an emulator to do the modeling. We apply active learning to ensure that it is sufficiently accurate for the inference we want to do. And then this plot shows the final exclusion that we put on ultra axion dark matter. And so our exclusion is the green line, which shows what is excluded at 95% credibility for the axion dark matter mass. And in particular, the main result is that we very strongly rule out this preferred range of masses for ultra axion dark matter, which is on the order of 10 to the minus 22 to 10 to the minus 21 electron volts.
Great. Thanks for the summary. Then let's go to questions. Daniela, please.
Hi, so first of all, great talk here. I really liked it. So I just wanted to check, I posted this in the asynchronous discussion as well, so feel free to ignore one of them. So when you say that you use a canonical ultralight axion, does that mean that you have only the kinetic and a mass term?
So what was that last word, Daniela?
Does it mean, so when you use the word canonical in your talk, does it mean that you only consider the kinetic and mass term for your, Yeah. So can I ask you why that is?
Yeah, so we just, this bound applies to what you might call the simplest formulation of an axion field or a light boson field. So it has just a quadratic potential with a small initial field displacement. And we consider the case where it is all of the dark matter. And so this is the preferred model that is motivated to explain the small scale discrepancies between simulations and observations on small scales. But you're absolutely right to imply that you could construct more complicated models that would have their own motivations, different potentials in particular. And in fact, there has been some other work showing that you could relax some of these bounds if you allowed for different axion models. In particular, there's a model which is referred to as extreme axion, where you have a very large initial field displacement, but perhaps there's some fine tuning to get such a large displacement. And actually, you end up with a boost in power relative to the CDM limit, and this can significantly weaken these bounds. And the other set of extensions I would like to mention is that you could consider mixed models, so allowing some subdominant fraction of the dark matter to be comprised of light axions. And again, you would relax these bounds. Yeah.
Great. If there are no immediate questions, I saw one, I think at least at the time of the talk, it wasn't, of the session wasn't answered yet, about the numerical efficiency and scalability of the Gaussian processes you use. I think it actually wasn't it by Marcos? Can't quite remember.
Yeah, I saw that question on the Slack. So this is about how when you have very large training sets, evaluating the emulator predictions can be computationally costly because you have this cubic scaling in the estimation, because you have to invert in a matrix with dimensions of the length of the training set. And that is essentially a fundamental to estimating the posterior predictive distribution given the Gaussian process model. Possible workarounds include having sort of clustered Gaussian processes. So you would have, bearing in mind that a lot of the, or most of the constraining power in a Gaussian process comes from the training points nearest to a given evaluation point. You don't necessarily need to include the training points which are very far away in the calculation of those matrices. And so that would be a way to reduce the dimensionality and speed up the algorithm. There's also been some work using sort of linear algebra to speed up some of these calculations. So there's a code called Celerite, which does this for Gaussian processes, but only in one dimension. And so at the moment, that wouldn't work in higher dimensional problems. But if you do have very large training sets, there's a good reason to have very large training sets. It may be more prudent to go down the route of neural network based emulators, where although the initial training becomes a bit more complicated and it's harder to get this sort of principled estimation of uncertainty, which you get with the Gaussian process, although you could use something like Bayesian neural networks. Once you have trained the emulator, the evaluation is very quick. It's a fraction of the time for a Gaussian process. But part of the motivation for the optimization part to this is to sort of reduce the size of training sets, to say that we don't need to have lots of training simulations filling the full parameter space, but to concentrate a few in the interesting parts of parameter space.
Thank you, Keith. I asked that question because we were thinking of using Gaussian processes for our work, but we ended up using neural networks because of this. Yeah. Thank you.
All right, I don't see any other immediate questions. So there was some, okay, actually no, Simon, please go ahead.
Hi, thanks. Sorry to cut you off, but here, really nice talk. So in this, you've been using the Lyman alpha forest auto spectrum. but the same thing could also work for cross correlations between Lyman alpha and another tracer if the simulation infrastructure exists to properly simulate correlated fields. Do you know if that infrastructure exists, or would it need more work to actually build that into the simulations before you apply this?
That's a very interesting question. The first thing that comes to mind is more from the data side, which is that we're measuring scales on Ks of about 20 on the smallest, which are obviously very small scales. And there isn't, well, I suppose it's the data side and it's a modeling side. So perhaps we could measure other traces to that K, but we don't trust the modeling. And the reason we can trust the modeling with the Lyman alpha forest is that these are fluctuations in the IgM, which are mostly sitting at mean density. And so we're less reliant on this slightly uncertain nonlinear modeling. The thing that comes to mind is perhaps if you had very high resolution CMB measurements. There have been some nascent measurements of CMB lensing cross Lyman alpha forest cross correlations. But again, it would be a question of matching up the requisite scales. But yeah, from the simulations, you would want to make sure that you understood the nonlinear clustering up to the smaller scale that you need to access, if that was appropriate.
Right. Okay, thanks.
Okay, maybe one question, like, since you already have this plot open, so what would be like your view on how to best close this gap in the constraints, either using your methods to improve them or other methods?
You mean further improving the bounds up to higher?
Yeah, to.
Yeah. So it's one striking thing we found was and I may as well show this slide again as well, is the dependence of the bound on the smaller scale that you access. So we did a test where you remove the small scale information, we find the bound weakens, and we argue that's consistent with you're no longer sensitive to the cutoffs of heavier axions because they're manifesting at higher K. So that suggests that if you had smaller scale measurements, even smaller scale measurements of the flux power, you may be able to improve the bound further. What would probably be, there's a couple of things that you would want to check, which is at some point there is an intrinsic smoothing from the IgM. So the fact that it has a finite pressure, you would probably hit up against that limit, and that's probably not much beyond the smaller scale that we're currently accessing. However, if you had external constraints on IgM parameters, so at the moment we're only exploiting the line of sight clustering, but if you had, for example, two quasars that were very, very close in the sky, you could measure the pressure smoothing scale by the transverse correlation between them, and there has been some sort of proto measurements along that direction. So if you could add in external constraints that kind of fix the IgM, then in principle you could look for the cutoffs from heavier and heavier axions and smaller scales. The other side then is that you need to really characterize your instrument very well, because you start to get into, you need very high resolution spectrographs to get smaller and smaller scales in the spectra.
Okay, understood. All right, thank you very much. I think then we're also at the end of our time. So yeah, I want to thank all the speakers, of course, again, for answering the questions. Thank all the participants also for having such a nice and active discussion.